We continue this evening with major news from the world of physics and astronomy. Physicists announced on Thursday that they have detected gravitational waves for the first time. The discovery confirms a part of Albert Einstein's general theory of relativity. Scientists say the breakthrough kicks off a new era of how we explore the universe. Here is a New York Times video looking at the observatory and how they detected gravitational waves.
Physicists long thought that gravitational waves would never be measured on Earth. But in Louisiana and Washington, two of the most sensitive detectors ever built have been waiting and listening. Astronomy has grown ears. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. Each detector has an L-shaped antenna with arms 2.5 miles long. Inside the ends of each arm, mirrors of ultra-pure glass are isolated from the noise, heat, and vibrations of the outside world. A beam of laser light measures the separation of the mirrors. The beam is split and sent toward mirrors at the end of each arm. If the arms are precisely the same length, the returning beams cancel each other out, and LIGO's detector sees no light. But a passing gravitational wave would stretch one arm and squeeze the other. The resulting discrepancy is tiny, a fraction of the width of a proton, but enough to misalign the beams and light up the detector in a rhythmic pattern.
Joining me now from Washington, Walter Isaacson, President and CEO of the Aspen Institute. He is the author of the biography, Einstein, His Life and Universe. Here in New York, Brian Greene, chairman and co-founder of the World Science Festival. He's also a professor of physics and math at Columbia University. Jenna Levin is an astrophysicist at Barnard College. Her forthcoming book on the search for gravitation waves is called Black Hole Blues and Other Songs from Outer Space. Dennis Overby of the New York Times has been covering the universe for more than 3 decades. He is the author of Einstein in Love, a scientific romance. I am pleased, very pleased to have all of them on the program. Dennis, explain it to us.
Well, basically 100 years.
What happened?
What happened?
Yeah. They heard something.
They heard 2 black holes collide 1 billion light years away from here. These were enormous, monstrous things. One was 36 times the mass of the sun. The other was 29 times the mass of the sun. These are like gigantic masses packed into a volume maybe the size of Manhattan. And they basically crashed together at half the speed of light. This really messed up space-time in a big way. And it created these ripples.
Is this what we call gravitational waves?
These are called gravitational waves that Einstein predicted 100 years ago, and physicists have been trying to figure out if they could detect them ever since. I mean, they have to go to superhuman lengths to detect these things.
Why have they been able to detect them now, Brian?
Well, they've been working on it for 40 years, so this is the end product of a major effort to detect these gravitational waves. Really, Einstein in 1915, to take a step back, he taught us that gravity is nothing but warps and curves in the fabric of space. But then if space can warp and curve, he realized if something were to disturb space, it should cause a ripple to go through space. For instance, if you start to tap a trampoline, you'll send ripples going along the trampoline. Yeah. So he predicted that we should be able to actually see these ripples in the fabric of space. Now, he actually flip-flopped. Sometimes he thought that prediction was right. Sometimes he became uncertain of it. But by the 60s, people who came along and did the analysis again, basically everybody was convinced that they are out there. But if black holes collide far away, they can really mess up, as Dennis said, the fabric of space right nearby. But if they're 1 billion light years away, that wave, it dilutes as it spreads out over 1 billion light years. So by the time it gets to Earth, it squeezes and stretches objects on Earth by a fraction of an atomic diameter. So these guys, the LIGO team, they were trying to detect the stretching and squeezing of a detector by less than an atomic nucleus. That's the challenge, and that's what they achieved.
Jenna, tell me, this needs to be confirmed. Well, that's
an interesting question. You can't actually confirm this particular event. The gravitational waves came and went.
Right.
So in some sense, they've confirmed it themselves because they have two instruments. It came from the southern sky. It hit one instrument in Louisiana. 10 milliseconds later, which is the speed of light travel time, it hits another instrument in Washington State. So the confluence of both detectors ringing and exactly the speed of light apart is a tremendous confirmation internally. Now, ideally, in science, you would have a completely unrelated experimental test. That just might not be possible here. I mean, we could hope that maybe some telescopes saw a flicker of something to confirm it, but two black holes are very likely to be dark. It's not impossible there would be a flicker of light, but two black holes are very likely to be completely dark. So this event came and went.
Walter, connected to Einstein, because of how much time you spent studying this when you were writing the book, how is it tied to the general theory of relativity?
The general theory of relativity is 100 years old. And it just says, as Brian described, that gravity is the curving of space and time by massive objects. Einstein's only great blunders are when he doubted his own theory. Because if you look at the theory of general relativity, people realize it would mean black holes exist. It would mean that the universe is expanding. All of these things. And every time Einstein said, well, maybe that can't be right. But indeed, general relativity, a century later, keeps being proven right. And it's just a most beautiful theory in the history of science. And it's just a miracle that, after a century, we can still be discovering how correct it was.
Then, as you have said, hearing a gravitational wave has opened up a new kind of astronomy. For the first time, we have ears as well as eyes on the heavens. Explain that.
Well, so the black holes colliding vibrate space at a frequency of a few hundred hertz, which is the tone of which we're speaking right now. So if you can get these signals, you can convert them directly into sound waves, and you can hear this chirp. That's the chirp, whoop, like that. Who knows what else they can hear? Because all these vibrations are going through us all the time, and this is like developing a whole new sense of seeing the universe. So hearing the universe, there might be things out there that theorists haven't even imagined yet.
Explain on that in terms of the pursuit. The pursuit of the universe now is
it's an incredibly powerful new tool because for thousands of years we have examined the universe, explored it by looking up and taking in light, waves of light. And as we've gotten better at it, we've built telescopes and more powerful telescopes. We gathered more and more light. We could see further and understood more and more about the universe. But light can be blocked, right? I mean, if I put up my hand, you can't see me right now because the light from my face can't get through my hand. So there are regions of the universe where you can't see because they're opaque. But gravity always gets through. There is no way to shield yourself from gravity. Put up your hand and gravity from the Earth still gets through it, right? Yeah. So gravity can't be shielded, which means if we want to, for instance, maybe look back toward the Big Bang itself, we can't see closer to the Big Bang than about 380,000 years because at that time the universe is filled with a charged plasma of particles light can't get through. Gravity can. So in principle, at one point in the future, who knows when it's going to happen, we may have a more powerful version of this kind of detector where we're not just seeing black holes collide, which is spectacular, but maybe we'll penetrate right back to the Big Bang by using gravity as our probe as opposed to light.
Jenna, when we say 1 billion light years, what do we mean?
Well, that's the distance light would travel if given 1 billion years. The event was probably more like 1.3 billion light years ago. So light travels at roughly 300,000 kilometers per second. I know Brian likes to quote it in miles.
671 million miles an hour, 6 trillion miles a year, whichever number you like. It's a lot.
And so how do dark holes collide?
Well, this is interesting. So black holes, these black holes may have formed. Presumably, best guess is that they formed as the death states of stars. And those two stars were in a system together. Jupiter's almost big enough to be a star, not quite, but you could imagine a two-star system like this. And then the stars die, and they live a very long life orbiting each other. But because they're ringing space-time the entire time, they're sort of slowly losing energy to the actually sloshing of space. And so they spiral together because of the gravitational waves. And after many billions of years, they eventually get close enough to collide. So we saw the final 200 milliseconds of the life of this pair.
Walter, how long did it take Einstein to come up with this theory?
Well, in 1905, his miracle year, he comes up with special relativity, and it takes him another decade to generalize it so that he can include gravity into it. He did it almost alone, although he had a lot of help with the math. But the interesting thing about this experiment, and the National Science Foundation should be credited, it was very crowdsourced. People around the world were involved. And, just east of Baton Rouge, there was one of the antennas. I think some hunters at one point shot at it. It's sort of the meeting of Duck Dynasty with general relativity. But so it was a very human endeavor. And I think that, one of the things we have to do to contrast what Einstein did a century ago in that decade in which he came up with general relativity is now we try to do science in so much more of a collaborative way. And we have to keep funding that notion of basic research, having the National Science Foundation and others do it. Otherwise, we won't have discoveries that'll turn into useful devices of the future.
Okay, I'm trying to figure out and to kind of associate this with another scientific discovery. I mean, is what we have just realized yesterday about the gravitational waves similar to, for example, discovering the structure of DNA? Is it that big?
Yeah, but the interesting thing is this was not a surprise for us. Everybody expected this to be the result. The surprise is that this team of scientists could pull it off and measure this tiny, tiny signal that confirmed ideas that the community basically had already agreed must be the case. But in terms of looking to the future, then yeah, I would say this is like the invention of the telescope.
I just want to add that this is one of the greatest examples of how science has done. When these guys started kind of imagining the idea of detecting gravitational waves in the late 60s and early 70s, it was not popular. It was very obscure. It started with one, then two, then three people, Ray Weiss, Kip Thorne, Ron Drever. They're really the guys who got this started. Ron came later in the 80s. But this is a tremendously difficult campaign. It wasn't popular. It was wildly obscure, and it was this obsession.
Why was it not popular?
Well, people didn't think it was possible. They thought it was phenomenally expensive. There had been some false claims of detections earlier that had turned the tide of the community against it. So it was tremendous what these guys did to stick at it and to bring in so many people. And now we have a team of 1,000 that pulled this off.
What might people be looking at to see if there are any flaws in this?
One test would be if they see more events.
Yeah, and that's a confirming tendency.
So the reason they believe this is because they've done supercomputer simulations of black holes colliding and neutron stars colliding and things that they know that might be out there, and these measurements fit the simulations exactly. What would be really interesting is the first time they get a signal that they haven't seen in a simulation, and they'll have to say, what is this? That will be the real eureka moment, I think.
That'll tell us.
It'll tell us there's something out there in the dark that we had no idea about.
I don't think you have a real worry about this being disproven. This is in Einstein's theory, and as everybody else just said, it had to happen. It was like when Einstein was asked when the eclipse observation proved general relativity right the first time, almost 100 years ago. Another great New York Times headline, "Lights all askew in the heavens." When Einstein was asked by a graduate student, what would you have thought if it had come out differently? He said, I would have felt sorry for the good Lord because the theory is correct. And we know the theory is correct.
The team spent 6 months on this data to ensure that what they were seeing was, in fact, the merger of these two black holes. So it's not that the theory could be wrong at this point. That would be shocking, absolutely shocking. But, yeah, could it be a false alarm in their measurement? Very unlikely. But bear in mind, a couple years ago, there was a false alarm. Yeah. There's another team that thought they saw gravitational waves in a different setting. Everyone got all excited, and that turned out to be a little premature. So they were quite careful this time around, and there's great confidence that this is correct.
And one of the things that they looked at right away was whether or not a hacker had gotten in and injected a false signal.
Make sure that was not true. But so what sounds does the universe make, and where does that fit into this?
So It's interesting, if you were actually floating nearby these two black holes colliding, in principle, it's possible that the wobbling of space-time would pluck your eardrum and you would technically hear the sound, even without a medium like air. And so, in some sense, these are closer to sounds than just an analogy. It's kind of also like an electric guitar. You record the ringing shape of the drum, and the analogy, space-time is the drum, and then you plug that record of the wave into a speaker system and you an amplifier, and you play it back as sound. So literally in the control room at LIGO, at the two LIGO sites, they listen to the detector. It's really quite charming, and you can kind of hear it moving. You can hear noise and rumbling. They can hear earthquakes. But what we're hoping for are these kind of cataclysmic astrophysical events. These have to be super high energy, lots of mass, sudden events. Stars exploding, black holes colliding. Brian was mentioning the Big Bang might have actually made a bang, although that might be very hard to hear because it could be extremely faint. Neutron stars, which are dead stars that didn't quite become black holes, if they have very tiny mountains on them, it's like a paddle swishing space-time, and it causes a kind of monotone. So there's a kind of panoply of expected sounds.
Walter, what did Einstein hope this would lead to?
Well, you know, Einstein's fingerprints are on all sorts of things we do. When I hit my iPhone to get an Uber, there's the GPS, or on space travel, or on semiconductors. But I think Einstein felt this would lead to us as human beings understanding our cosmos. And to him, that was the great quest. It wasn't like, let's invent a laser or let's invent a microchip. And that is the essential nature of humans, is to say, okay, what is it that is this universe, and to try to understand it. And I think that's all he was hoping it would lead to.
Having this new tool, gravitational waves, is really a new tool to explore space and time.
And what might we find?
Well, we might find that the theory and the more refined observations that no doubt will be made in the future, they may not completely agree. Einstein may be in the right direction, but it might not be the full story. And there's many reasons for thinking it won't be the full story.
You know, if you think about when Galileo first looked through a telescope, he was only considering our solar neighborhood. I mean, he didn't foresee galaxies, you know, collections of hundreds of billions of stars, or quasars, gigantic supermassive black holes powering jets. I mean, all of this came with the telescope. So right now we've got a new kind of an instrument that's not taking pictures. It's recording space-time. So maybe there are dark things that we're just looking at the things we know about, as did Galileo, but there's stuff out there that we had not foreseen.
But what might be out there?
Jana, please.
Well, you know, Brian and I have written papers together on, like, dark energy. Now, it's extremely unlikely that dark energy could generate gravitational waves and the things we've thought about, but I think we have to think harder. This is an example of something that's genuinely dark, meaning it's not something you can take a picture of with a telescope. And so there's also dark matter. There's things that we should be thinking about, at least have hints, we have hints towards, that, I don't know, maybe there's some way that they would only be represented through the sounds.
So where does this send your curiosity, Walter?
I think one thing you want to know is, how did it all begin? And I guess everything we do gets us a tiny step closer to the origin, the Big Bang. I don't know if we'll ever figure it out. I don't know if we'll ever have a unified theory, the way Einstein was hoping, that would tie together all the forces in the universe. But everything we do gets us a little step closer to that Holy Grail.
Yeah. So the Holy Grail is figuring out how it all began.
That is, I think, the deepest question in all of modern science, really. Why is there a universe at all, right? So everything else is somehow subordinate to that question.
One speculation about gravitational waves, which is that it's been speculated that alien civilizations could use them to communicate, because you can traverse the entire universe with these waves.
Gravitational waves may enable us to communicate with civilization somewhere else.
Right. Try getting your congressman to pay for those black holes that were going to vibrate, but you know. That would be
this is a good day for physicists, isn't it?
It's a good day for Einstein.
An extraordinary day. I mean, for any of us who care about the future and care about science and need a clarion call to deepen our commitment, this is it. Thank you all very much.